Welcome to today's Explainer. We're going to be opening up what a lot of people consider the absolute black box of industrial electrical troubleshooting. Honestly, I want you to think of this not just as, wires and machines, but as a thrilling detective process. Because every single time a piece of machinery goes down on the production floor, a mystery is born. So today, we're exploring exactly how master technicians approach this mystery to hunt down the real root cause. Here is our roadmap. We'll start with the troubleshooting mindset, move into the six-step framework, check out some circuit navigation strategies, dive deep into in-circuit component testing, and finally, bring it all together in the unified diagnostic workflow. All right, before we get into the framework itself, let's tackle a very real-world question. Why on earth do technicians keep fixing the exact same machine twice? Well, picture this. A maintenance tech arrives at a stopped conveyor belt. Without even pausing to think, they immediately start swapping out the motor starter because, quote, that's what it was last time. They are literally just firing the parts cannon, completely skipping right over the actual root cause of the failure. So the crucial takeaway here is that true professionals just don't guess. No way. They rely on a strict, systematic process to gather hard evidence before they ever act. Effective troubleshooting is methodical, it's not reactive. Every single decision has to be driven by process, not just a gut feeling or a hunch.
Section 1. The troubleshooting mindset.
Now, it is absolutely vital to remember that a tripped breaker, a stopped motor, or a dead indicator light, well, that's merely a symptom. It's not the crime itself. Your target is always the underlying failure, rather than just forcing the machine back into operation for a few hours. And reaching that target requires gathering information, checking fault codes, talking to the operator, doing visual inspections, all of this long before you ever let a meter lead touch a terminal. Let's move into Section 2, the six-step framework. So these are the 6 steps that govern every single troubleshooting job, right from the moment the call comes in to the exact second the work order is closed. The workflow kicks off with observing and defining the problem, followed by developing a cause list, and then determining the most probable cause using basic logic and system knowledge. Skipping these first 3 observation steps, that is exactly why technicians end up right back at the same broken machine. You absolutely must form a theory before you test it in step 4 and fix the root cause in step 5. But listen, fixing the machine isn't the end of the line. Step 6 is documentation. I really want to emphasize that logging the fault details, the corrective actions, and the exact parts you used into the CMMS, that's a professional obligation. Over time, these records build an incredibly valuable fault history. So this doesn't just close out your current job, it dramatically accelerates future fixes for everyone. All right, Section 3, Circuit Navigation Strategies. We've got a whole menu of choices here, and honestly, no single strategy is always the best. If you know the machine like the back of your hand, use symptom-and-cause. If it's a completely unfamiliar system, use the output-back method, just working backward from the load to the source so you stay oriented. And if you're dealing with a massive 24-component PLC control circuit, use the half-split method. It acts just like a binary search, eliminating half of the suspect circuit with every single measurement. It literally slashes the number of tests you have to perform. Now, you probably noticed the shotgun method on that list, which is essentially swapping out cheap parts as fast as humanly possible. I really need to warn you about this one. If you absolutely have to use the shotgun method because extreme downtime costs demand it, you are not off the hook. You haven't actually finished the job until you take those replaced parts and individually bench test them later. Because without that critical follow-up, the root cause remains a complete mystery. Let's dive into Section 4. In-circuit component testing. Okay, before we even think about touching a meter, safety has to be embedded in your workflow. You must respect your de-energized boundaries with strict lockout/tagout procedures and ensure every piece of gear is properly cat-rated for the environment before you even approach a live panel. This is non-negotiable. Safety ensures you actually get to go home after solving the mystery. Here are the 5 precision tools we use to gather hard evidence and basically confirm or eliminate our theories from earlier. Each of these serves a very distinct diagnostic purpose, operating under specific energized or de-energized conditions, and they yield completely different types of clues. Let's look at the first 2, voltage and current testing. Both of these are energized tests. Now, if you get a voltage test of 0 volts across an active component's input terminals, say a contactor coil, that doesn't necessarily mean the coil is dead. It actually indicates an upstream fault. On the flip side, current testing uses a clamp-on ammeter. If your motor is drawing current significantly above its full load amperage, well, that strongly points to mechanical binding, an excessive load, or maybe a phase imbalance.
So the absolutely crucial point when we move to resistance testing is that you must completely de-energize the circuit. Not only will live voltage totally fry your meter, but you also have to watch out for hidden parallel paths. Actually, scratch that. It's not just watching out. Another component wired in parallel will actively trick your meter into reading a lower resistance than the component's actual value. Always, always isolate the component first so you don't accidentally throw away a perfectly good part.
Now, voltage drop testing is special. It's an energized test performed while the system is actively under load. So why is this so crucial? Because a connection can show completely normal voltage on both sides during a standard voltage presence test, but then totally fail the second a load is applied. Voltage drop testing exposes that hidden, excessive resistance that you would otherwise completely miss. It's a real game changer. I want you to lock this concrete data point into your brain right now. 0.5 volts. When you perform a voltage drop test across a connection, a healthy connection should show less than 0.2 volts of drop. If your meter reads anything over 0.5 volts, you need to stop and investigate immediately, because that connection is definitively failing under load. Bringing us to Section 5, the Unified Diagnostic Workflow. See, these aren't just isolated skills. They form a completely unified system. Think about it like this. The six-step framework is how you think about the entire job. The 4 navigation strategies determine how you physically move through the circuit. And the 5 in-circuit tests, that is how you get your definitive proof. Understanding how these 3 layers fit perfectly together is what allows you to work faster, make way fewer errors, and deliver repairs that actually hold up over time. Which brings us to our final big question for this explainer. How can you apply the systematic root cause thinking to complex problems in your own industry? Because whether you work with industrial electricity, software engineering, or even business operations, the lesson is exactly the same. We have to stop reacting to symptoms, stop guessing, build a unified workflow, gather your evidence systematically, and start investigating like a master technician. Thank you so much for exploring this with me today, and keep questioning the root cause of everything.